all three parts, something like that. Okay, so basically this topic, chapter 6, will cover on the thermal power plant. Okay, so this part we will discuss on the Brayton cycle or gas turbine. All right, so introduction to power plant. So basically, a power station is a power plant in which heat energy is converted into electric power. So most power stations contain one or more generator, a rotating machine that converts mechanical power into electrical power. So types of power plant, we have several types of power plants. First, known as gas turbine power plant. So it uses gas, natural gas as a working fluid and as a source of combustion. Steam turbine power plant. So basically, the working fluid for change phase from liquid to vapor, and normally use water. Nuclear power plant. So basically, it's the source of energy come from the nuclear reaction. And fourth is hydroelectric power plant. So basically, we use a dam for falling water. And number five is solar power plant. So basically, this is a renewable energy. So the source is from the solar. And number six is geothermal power plant. So basically, the source of energy is come from the earth crust, which is the geothermal. Okay. And number seven is tidal power plant. So basically, it's also the energy source come from the tides. And lastly is from wind power plant. So basically using a wind turbine. So basically in this topic we discuss on the gas power plant and steam power plant. Okay, gas turbine. So basically gas turbine engine used for power production and generate a thrust for jet propulsion. Basically also this engine is used by the jet, okay, aeroplane. So the gas turbine have a great power to weight ratio compared to reciprocating engine. Basically, it's a much more smaller than the reciprocating engine and produce more power. Okay, so the main disadvantage is compared to a reciprocating engine of the same size, they are very expensive. Okay, because of they spin at such a very high speed, and because of the high operating temperature, designing and manufacturing gas turbine is very tough problem from both the engineering and also the material standpoint because of the higher temperature and also the higher speed. So gas turbine also tend to use more fuel when they are idling, and they prefer a constant rather than fluctuating load. So basically, they're using only at a constant load lah. Okay, working principle. So basically, gas turbine engine derive power from burning fuel in the combustion chamber and using the fast flowing combustion gases to drive the turbine. So it is an internal types of combustion engine. So it sucks in air from the atmosphere, compressed, and the fuel is injected and ignite. So the gas expand during work and finally exhaust outside. So basically, this is the diagram for general gas turbine principle. So you see that this is the air intake. So air move in here. So this is the compressor to compress the air. Okay. So the compressor used is to increase the uh, high pressure. Okay, the pressure of air increase, and the high pressure is being combust inside the combustion chamber using the fuel. So basically the product of the combustion chamber, the thrust, okay, from the combustion chamber will move the turbine, okay, and lastly the exhaust gas will be left outside. So in a thermodynamic way, so basically this is the sketch, the diagram. So we have a compressor, so we have also a turbine. So basically, so the fresh air comes in. Okay, so from 1 to 2 is a compressor process, 2 to 2 to 3 is a combustion process, okay, whereby we assume heat being added here. And lastly is from 3 to 4, which is the turbine process. Okay, right. So the ideal for gas turbine engine. So basically the introduction of Brayton cycle. So Brayton cycle, or also known as Joule cycle, is the air standard ideal cycle approximation for the gas turbine engine. So basically we assume Brayton cycle is the basic ideal for gas turbine. So the combustion process is replaced by a constant pressure heat addition process from an external source, and the exhaust process is replaced by a constant pressure heat rejection process to the ambient air. So we have four processes. Okay, so process 1, 2 is the isentropic compression. So this is the isentropic compression. Okay, so as we look in TS diagram, so 1, 2 is a isentropic compression. So S is a isentropy, entropy. So this is a isentropy, constant heat addition, sorry, constant compression. So 2 and 3 is a constant pressure heat addition. So heat being injected here, process 2, 3. So process 3 to 4 is an isentropic expansion in turbine. So this is the turbine process take place. Process 3, 4. Process 3 to 4. Turbine process. Okay. So the last will be the constant pressure heat rejection. So from 4 to 1, okay, to complete the cycle, heat will be rejected. Okay. So we assume here is a heat rejection. Although in the real one, we have up to only 4, but in normal cases, we assume that the 4 to 1 is we have a heat exchanger where the temperature and also the pressure is come back to normal. Okay, so we have a cycle process from 1 to 4. Okay, so basically Brayton cycle, in Brayton cycle, we use air. So basically the related formula for this process, the whole entire process, is the ideal gas cycle. Okay, so basically all the relative formula is for air. Okay, okay, so before I forgot, so this air process has been introduced to you in chapter 3 and chapter 4. Okay, so you can refresh back for this formula lah. Okay, so thermal efficiency and backward ratio. Okay, so thermal efficiency of the ideal Brayton cycle is as a function of pressure ratio. So this we have a pressure ratio. So pressure ratio is from the compressor. Okay, so basically the higher the the pressure ratio, your efficiency of the Brayton cycle also will increase. But as you see, 20 is your starting to linearize. Okay, so flat. So basically there's this curve starting to flat at pressure ratio 20 and above. So basically the best type is from 5 to 20. We call it as a typical pressure ratio for gas turbine engine. So basically all of the gas turbine engine will operate under the pressure ratio 20 to 5. Okay, so also we have a backward ratio. So pressure backward ratio is some of the uh, work turbine is used for compressor, because as you look into this sketch, you have a same shaft connecting from the compressor with the exhaust. So that's why we call it the compressor use the kinetic energy from the turbine. So the same shaft, okay, uh, the same size shaft from the compressor and turbine. So basically the compressor will operate using the energy from, oh sorry, the energy or the work from the turbine. So that's why we have a backward ratio. So the backward ratio is the ratio between the work of compressor and also from the turbine. All right, so that we call it as a backward ratio. Sample problem 6.1. Okay, so sample problem 6.1. The ideal air standard Brayton cycle operate with air entering the compressor at 95 kilopascal, 22 degrees Celsius. The pressure ratio RP given directly, okay, is 6 to 1, and the air leave the heat addition process at 1100 Kelvin. Determine the compressor work and the turbine work per unit mass flow, the cycle efficiency, and the backward ratio. Assume constant specific heat at room temperature. Okay, so look back at this question. We should know that given directly is the constant specific heat at room temperature. So we assume this entire exercise use the constant specific heat, which is Cp specific heat at constant pressure is 1.645. Okay, so basically this is the specific heat used for this exercise. So bear in mind, the specific heat will be fluctuating depending on the temperature. Okay, so as in this question is constant, so we use at room temperature lah. Okay, so given directly is your pressure and also temperature and temperature 1. Okay, so T1 here is given directly and temperature T, the maximum is also given directly. Okay, so the first is to know to locate each point the pressure and temperature. So that is the task. Because from this point, each point pressure and temperature, we can calculate the efficiencies and also the backward ratio. So the first task given here, the point here, we must have 2 points, because 2 point here we can refer to the tables if we refer to tables, but in this exercise we use formula. So basically we need 2 data for each point at least. Okay, so given in point 1 is a pressure and temperature. So from this pressure and temperature we can calculate the point 2. Okay, so using this equation, okay, we can determine what is the temperature at point 2. So using the formula, and we assume this is the isentropic compression, so we know that temperature at point 2 is 482.21 Kelvin. Okay, before I forgot, so basically the K we assume is 1.4. Okay, so because it's a isentropic. Okay, so process 3 to 4. Okay, so point 2 we have the temperature here. So as we want to know uh, the pressure too, also we can know by using the pressure ratio. So pressure ratio is 6 to 1. So basically the pressure ratio, this is the compressor. So basically pressure ratio P2 1, P2 is 6 times from P1. So directly we can know what is the value of pressure at point 2. It is a 6 times higher from pressure 1. Okay, all right. So process 3-4. Okay, so 3-4 we only know the temperature at T3. Okay, so basically the pressure ratio from pressure 3 to 4 to 1, also the 6 to 1. Okay, because this is the you know back. Okay, so this is a turbine ratio. We only involve two pressure. Okay, two pressure line. Okay, so basically two pressure line. So the ratio is constant because this is the pressure line 1, this is the pressure line 2. So we have two pressure line, so the ratio is also remain the same. Okay, but it's backward. So this is the P4 over P3. So we have 1 over 6. Okay, so we can determine what is the temperature at point 4 because for temperature at point 3 is given directly in the question. So from this, we can know each point temperature and also the pressure. So from this value, we can calculate what is the uh, work compressor and also work turbine. And from this work compressor and work turbine, we can calculate the backward ratio. Okay, so work compressor, work turbine, we can calculate the backward ratio. Okay, for the efficiency, we must know the work net. So work net is work turbine minus work compressor and divided by total heat injected. So total heat injected is using CP, okay, constant pressure, and temperature 2, temperature 3 minus temperature 2. So because this is the point, you in temperature 3 minus temperature 2. Okay, so we have the heat injected. Okay, so from this heat injected and also the work net is work turbine minus work compressor. So we can get the efficiency of the Brayton cycle is at 14.1%. Okay, all right. So deviation of actual gas turbines from idealized one. So because of the irreversibility in turbine, so we have a compressor, pressure drop, and heat loss, etc. So we have isentropic efficiencies. So which means that the efficiencies will be deviate from the actual one because of many factors. Okay, so basically we need to know what is the isentropic efficiencies. Okay, so for isentropic compressor and turbine, so we have this equation lah. Okay, so we have isentropic 2.2 and 2. This is the actual one. This is the isentropic condition. So this is the actual. Okay, so from the enthalpy of at H2A actual, okay, so we can get the efficiency for compressor. Okay, so H2S pendek, ini yang pendek, ini yang panjang. Okay, so H2S minus enthalpy 1 divided by enthalpy actual minus enthalpy 1. Okay, for turbine, okay, so okay, so basically here be aware that the actual is at the top because the turbine is produced much smaller compared to the entropic one, the idealized one. So normally turbine will produce less power output compared to the idealized one. So the actual will be shorter compared to the isentropic ones. Okay. Sample problem 6.2. Okay. So a simple Brayton cycle using air as the working fluid with a pressure ratio of 10. So here given the directly pressure ratio is 10. So the minimum and the maximum temperature in the cycle are 295 Kelvin and 1240 Kelvin, assuming an isentropic efficiency of 83% sorry, for the compressor and 87% for the turbine, and using constant specific heat at room temperature, determine A, air temperature, B, net work output, and lastly C, thermal efficiency. So given, okay, so this is your pressure ratio RP, so P2 over P1. So bear in mind we have only two pressure line. Okay, so basically the pressure ratio is 10. Okay, so at point 1 given directly, and also point 3 the temperature also is given. Okay, from here this is your given isentropic efficiency is given directly for compressor and turbine. So here we have we need to determine what is the actual temperature for these figures. Okay, all right. So this is the formula related. Okay, first of all, we need to know, bear in mind, and when we dealing with this turbine, sorry, from this cycle, so we need to determine each point temperature or the pressure each point for the entire point lah. Okay, so if you have 4 points, you have to determine what is the pressure and temperature for each of the points. Okay, so for process 1, 2, we have a isentropic conversion. So using this equation, okay, same. So we can determine this is your temperature actual. Okay, so because the firstly we calculate is isentropic. By using the calculation, this equation is a isentropic conversion. So what is the value is isentropic value. So by using the given efficiency, isentropic efficiency, okay, so we can determine the temperature at actual. Okay, okay. Process 3, 4 also same. We have the pressure ratio, okay, and we can determine what is temperature at 4S. So this is the temperature at isentropic point 4. Okay, so from this equation, you can determine the temperature for S. Okay, and by using the efficiency for turbine, okay, so we can calculate the temperature actual at point 4. So we have the actual point 4. Okay, so from this, okay, we can calculate the actual turbine, work turbine, and also actual work compressor. Okay, and also the heat injected to the system. So from work turbine, work compressor, and heat injected, we can calculate the efficiency. So the work net is work turbine minus work compressor. So work net here, so divided by Q in, heat injected into the system. So we can have the efficiency of 30.81%. Okay, right. So development of gas turbine. So the higher temperature in the cycle is limited by the maximum that the turbine blades can withstand. So basically, the turbine blades that rotate at higher speed, so there must be some limit because of the material itself. So this also limits the pressure ratio that can be used in the cycle. The air in gas turbines supply the necessary oxidant for the combustion of the fuel, and it serves as a coolant to keep the temperature of the various components within safe limit. Okay, so basically an air-fuel ratio of 50 or above is not uncommon. So there are possible ways to improve the cycle. So number one is to increase the turbine inlet. temperature. So basically, possible way is to increase temperature. Number two is to increase the turbomachinery component, such as turbine and compressor. The higher the efficiency of turbine and compressor, the higher of the total gas turbine. Okay, so adding modification to basic cycle, such as intercooling, regeneration, or recuperation and reheating. So this is the idea for development of gas turbine, which means that we increase the temperature, okay, at up to T max, temperature max. So above than this, we have problem because of the material. Okay, so we have the T max and T mix, min, sorry. Okay, so as we're talking about the development of Brayton cycle, so we talk about regeneration as to increase the efficiency of Brayton cycle. So in gas turbine engines, the temperature of the exhaust gas leaving the turbine is often considerably higher than the temperature of air leaving the compressor. So therefore, the high pressure air leaving the compressor can be heated by the hot exhaust gas in a counterflow heat exchanger or a regenerator or recuperator. Okay, so basically this is your regenerator. We have the heat exchanger. So the heat exhaust turbine will be used to reheat the air before entering the combustion chamber, not before entering the compressor, because we will tear down all the compressor component and it will place after the compressor. Okay, so the thermal efficiency of the Brayton cycle increase as a result of regeneration, since less fuel is used for the same work output because the temperature is high. Okay, so basically the process, this is your diagram. So from process 2 and 3, we have a 5. So 5 is Q regeneration helped by the heat exchanger. So we call as a Q regen, and 5 to 3 is heat being added. Okay, so basically only Q in here is the actual or the necessary heat being added. Compared to before this, the entire 2 and 3 is the heat being added from this regenerator. So only half of the heat needed, okay, to produce the same efficiency. So from this here we have the Q save, which is the same as heat being regenerated. Okay, so that is the basic idea of Brayton cycle with regeneration. Okay, so the effectiveness regeneration is defined as the ratio of heat transfer to the compressor gases in the regenerator to the maximum possible heat transfer to the compressor gases. So Q regeneration, heat regeneration, actual is your enthalpy at zero point 0.5 minus at zero point 0.2. So this is your heat being regeneration. So that is the actual. But in the maximum, the actual maximum is from the 5 dash here. Okay, so the maximum for Q regeneration is from H max 5 point minus H2 enthalpy at zero point 0.2 is equal to enthalpy at 0.4 minus enthalpy at 0.2. So the efficiency of regeneration is the Q actual regeneration actual divided by heat regeneration maximum. Okay, so this is your formula. Okay, so for ideal gases using the cold as standard assumption with constant specific heat, the regenerator effectiveness become this equation. This is we using the temperature at each point. Okay, okay. So basically the efficiency of regeneration also we can use this equation. Okay, right. So the thermal efficiency depend on the ratio of of the minimum to maximum temperature as well as the pressure ratio. So regeneration is most effective at lower pressure ratio and low minimum to maximum temperature ratio. So the question is, can regeneration be used at high pressure ratio? So if you have the answers, you can comment below. Okay, so this is the efficiency for Brayton cycle with generation and also without generation. Okay, so we see that at lower pressure ratio with generation we have a higher efficiency. Higher pressure ratio is near to similar. Okay, sample problem 6.3. Air enter the compressor of a regenerative gas turbine engine at 100 kilopascal and 100 kilopascal and temperature at 300 Kelvin and is compressed to 800 kilopascal. Okay. The regenerator has an effectiveness of 65% and the air enters the turbine at 1200 Kelvin. For a compressor efficiency of 75% and a turbine efficiency of 86%, determine A, the heat transfer in the regenerator, B, the backwork ratio, C, the cycle thermal efficiency. So assume air is an ideal gas with constant specific heat. Okay, so the question is to find the heat transfer, backwork ratio, and also the thermal efficiency for the system. So this is the formula involved in this question. Okay, bear in mind, come back to the normal procedure in order to solve this question. So we must determine each point, the temperature and also the pressure. Okay, so for pressure 1 and pressure 2, we have the relationship is by using the pressure ratio. So from this figure, the pressure 1 and pressure 2 has been given. Okay, so we have the pressure ratio is 8. So given directly in the question. Okay, so from this pressure ratio, we can determine the temperature at isentropic point 2. So from isentropic point 2, we have 543.43 Kelvin. So from this temperature, isentropic temperature, so we have the actual temperature by using the uh, isentropic efficiency for the turbine. Okay, sorry, compressor, isentropic efficiency of the compressor. So the actual temperature point 2 is 624.57 Kelvin. Okay, so this is a process 1, 2. So process 3, 4. Okay, also for process 3, 4, the temperature at point 3 is given directly in the question. So we can determine what is the temperature, isentropic temperature, point 4, okay, by using this equation. Okay, so we have the value. Okay, so from this value also we can determine the actual temperature at point 4 using the isentropic efficiency for the turbine. So from here, the actual temperature at point 4 is 737.71 Kelvin. Okay, so from the regeneration, the temperature, we have all the temperature, so we can determine the point 5, because the A generation given is effectiveness regenerated is 65% given directly, so we have the 65%, so we can determine the temperature at point 5. Okay, so from point 5, okay, we can calculate the total, what is the heat being injected to the system. Okay, and also the work compressor we can calculate from the previous temperature. Okay, and also work turbine. So from this equation we can determine the back work ratio, work turbine divided by work compressor divided by work turbine. So we have the back work ratio is at 70.2%. So lastly, the efficiency of the system. Okay, so this is your work net divided by heat injected. Okay, we have 27.44%. Okay, right. Okay, so here is a multiplication of intercooling, reheating, and also regeneration. Okay, so we have a multiple process. So we have the compressor 1 and compressor 2. We have a compressed intercooler, which is to normally from point 1 to point 2, the temperature of air slightly increase. So if we have a double compressor, so from point 2, we have, as the air is being increased, so point 3 is also same with point 2. If we move out the intercooler, so point 4, we have a very high temperature. Okay, so basically in the compressor working at a high temperature, we will we have a higher tear and wear. So that's why we need intercooler in order to lower down the temperature at point 3 as same as point 1 in order to safeguard the compressor. At point 4, assuming that point 4 temperature is same with point 2. Okay, because we assume this compressor is identical. Okay, so at point 4 and point 5, before entering the combustion chamber, we have a regenerator. So that's why point 4 need to reheat using the exhaust gas. So at point 5, the temperature is much higher compared to temperature at point 4. Okay, and then combustion takes place at point 6. So entering the turbine. So at turbine 1, turbine 1. So this is your exhaust gas. Okay, and then reheat again, because we assume the temperature at point 8 is similar with temperature at point 6, because we want that this turbine 2 have the same output with the turbine 1. Okay, so point 9 exhaust gas is released to the generator back. So the diagram for this TS diagram, we have this lah. Okay, so this is point 1 static. Okay, at point 2 with the compressor. So the temperature point 2 and point 4 we assume same. And point 1 and point 3, the temperature also we assume same. Okay, same with temperature at point 6 and point 8, and point 7 is the same with point 9. So point 5 is the regeneration. Okay, so the Q regen is at point 5. So the total added is at point 5 to 6, heat added, and also 7 to 8. So this is the reheater. So heat added is at these 2 points. Okay. All right. the Brayton cycle with intercooling and reheating and regeneration. So we have a multi-stage compression with intercooling. So the work required to compress a gas between two specific pressure can be decreased by carrying out the compression process in stages and the cooling the gas in between. This keep the specific volume as low as possible. So multi-stage expansion with reheating. So it keeps the specific volume of the working fluid as high as possible during an expansion process and thus maximizing the work output. So we have intercooling and reheating because it always decreases the thermal efficiency unless they are accompanied by regeneration. So that bear in mind why we need the regeneration. Okay, if you have the answer, you can comment below, right? So in this example, we have multiple reheating, okay, and multiple intercooler, right? Sample problem 6.4. Okay, problem 6.4. A gas turbine with intercooling and reheat operates at steady state. Air enters to the mouth of identical compressor at 300 Kelvin respectively, and both of identical turbine at 1400 Kelvin respectively, with a mass flow rate within the cycle is 6 kilos per second. So the pressure ratio across the two-stage compressor and the two-stage turbine is 10 respectively. So the isentropic efficiency of each compressor and turbine stage is assumed to be 100%. Assuming that there is no pressure loss during intercooling, combustion, and reheating process, and by using the cold air standard assumption, so first is to sketch the S diagram for this regenerative Brayton cycle. B. Determine the thermal efficiency. C. Determine the net power developed in kilowatt. Okay, so we have given temperature at 0.1 and 0.3. We assume identical, so therefore temperature is same. And 0.5 and 0.7 is also identical. We assume this is the same. So this is your diagram, TS diagram. So 0.1 and 0.3 is the same temperature, 300. Okay, so it's given directly in the question. Okay, and the outlet is at 0.4. Okay, so normally 0.5 is at the regeneration. So here we don't have any regeneration. Okay, so basically before example before this we have the regeneration. So here we don't have any regeneration. So the heat, okay, primary, we have two types of heat ejected. Okay, we call it as a heat primary and heat reheat. Okay, all right. So pressure from, okay, if we have multiple pressure ratio here, so pressure ratio 0.1 and 0.2. Okay, so 0.1 and 0.2 and 0.3 to 0.4 is the square root of 2. Okay, 10 is the pressure ratio and the square root of 2. Okay, and we have 3.16. Okay, so this you, why? Because we use, before this we don't have the square root. Okay, so basically this is the usage for multiple. If let's say for example we have three compressor, so this is the square root of 3. Okay, so basically if we have 4, square root of 4. Okay, so in this example we have 2, square root of 2 only. Okay, same with at the turbine. So P7, so 5 to 6 and 7 to 8, also same. So this is the regeneration. So bear in mind, before this, also we have, but this is square root of 1. So that's why we don't write down. Okay, so if we're dealing with 2, so we have a square root of 2. Okay, all right. So we need to determine each point, temperature and pressure for each point. Okay, so the efficiency of this system. Okay, so with work net and in. So work net is work turbine out minus work turbine, work in. So the total is work turbine out. Turbine out is, we have two turbines, so they're identical. So which means that we have 2 times work turbine. Okay, so from this equation, so we can calculate. Okay, all right. So then we know the temperature at 0.6 and 0.8. Can, okay, using the same figure lah. Okay, T5 7. Okay, so from this T5 and T6, we use the something like this. Yeah. Okay, so from this figure we can determine the sorry, each point temperature. Okay, all right. So calculate first what is the temperature at 0.6 and 0.8, 0.5 and 0.7. So substitute in this equation, so we can have the work turbine out. Same with work turbine 8, work in. So work in is a work compressor. Okay, so we have two compressor. So from T2, T1 and T4, T3. So 2 times 2 work in compressor. Okay, all right. So Q in, heat injected. So we have two types, primary and reheat. Okay, so primary is from T5 and T4, and for reheat we have T7 and T6. Okay, so from this equation, okay, T5 also we can calculate. 5 we have, okay, so and also T6 we can calculate. T6 we can calculate using this equation. Okay, isentropic compression. So substitute in this general equation. Okay, we can get the figures. Okay, so this is your answers. All right.